Last video we have discussed about definition and formation of partial differential equation. In this video we will learn about types and solution of partial differential equation. The equation which is function of x, y, z, p, q is known as general form of partial differential equation and it is denoted as fx, y, z, p, q equal to 0. The partial differential equation are of two types, linear and non-linear. If p and q are linear, or we say the order and degree of partial differential equation is 1, then it is linear partial differential equation. For example, px plus qy square equal to z is linear partial differential equation. If p and q are not linear, or we say the order and degree is more than 1, then it is non-linear partial differential equation. For example, p square plus q square equal to 1 is non-linear partial differential equation. Now the solution of partial differential equation. We know that partial differential equation is formed by eliminating constants. So the partial differential equation f x y z p q equal to 0 is derived from phi x y z a b equal to 0. And solution of f x y z p q is phi x y z a b equal to 0. Now the different kinds of solutions are complete integral, particular integral, general integral and singular integral. Now the complete integral, it contains as many arbitrary constants as the number of independent variables. For example, phi x y z a b is equal to 0 is complete integral because it has two independent variable xy and two constants a and b. When a particular value is assigned to the constant of complete integral, it becomes particular integral. Now the general integral, it contains as many arbitrary functions as the order of partial differential equation. When we eliminate the constant present in complete integral, it becomes singular integral. Now let's see how we find the solution of linear partial differential equation. If the partial differential equation is the form of pp plus qq equals to r, then it is known as Lagrange's linear partial differential equation. Here p, q, r are the function of x, y and z. Small p is del z by del x, small q is del z upon del y. Now the solution of this Lagrange's linear equation is, first we have to find Lagrange's auxiliary equation. Lagrange's auxiliary equation is dx upon p equal to dy upon q equal to dz upon r. Now if we can easily separate the variables, then we use method of grouping. In this method we consider two equations, dx by p equal to dy upon q or dy upon q equal to dz upon r or dx upon p equal to dz upon r. We solve any two equations and find two solutions that are u equals to a or v equals to b. And the solution of partial differential equation is f u comma v equal to 0. So this method is known as method of grouping. So let's see the example. Solve the following partial differential equation. So here we have yq minus xp equal to z. So we see this equation is PP plus QQ equals to R. The coefficient of small p is minus x, the coefficient of small q is y, and equal to some z. So we have capital P is minus x, capital Q is y, and capital R is z. So we write auxiliary equation as dx upon minus x equal to dy upon y and dz upon z. We see variables are separable. We can easily separate the variables and integrate it. So we choose first two equations, dx upon minus x equal to dy upon y. So by variable separation method we integrate the terms and we get xy is equals to a. Similarly, we choose the last two equations, that is dy upon y equal to dz upon z, and again we integrate the terms and get y upon z is equal to b. So here we have two solutions, xy equal to a and y upon z equal to b. So by combined solution of partial differential equation we write function of xy comma yz is equal to 0. So this is the solution of linear partial differential equation by the method of Lagrange's partial differential equation. Now the another example is y square p minus xyq equal to x z minus 2y. It is again in the form of pp plus qq equals to r. We just find capital P is y square, capital Q is minus xy, and capital R is x z minus 2y. So we write auxiliary equation dx upon y square equal to dy upon minus xy equal to dz x z minus 2y. Again it is seen that variables can be separated easily. So we take first two terms and integrate the terms, and after simplifying we get x square plus y square equal to c1. Next again we choose another two equations, that are dy upon minus y equal to dz upon z minus 2y. Cross multiplying the terms and we get 2y dy equal to y dz plus z dy. And by integrating these terms we have y square minus yz equal to sum c2, and we write the solution as x square plus y square equal to f function of y square minus yz. This is the method of Lagrange's differential equation. Again we have another example, x square minus yz p plus y square minus zx q equal to z square minus xy. Here again we write auxiliary equation, and here we see we cannot separate the variable easily and variable separation method is not applicable. So when we see such type of problem we try we solve the terms in cyclic order, just as dx minus dy, dy minus dz, dz minus dx, numerator and denominator also. So we have dx minus dy and same as x square minus yz minus within bracket y square minus zx. When we solve it we get x square minus yz minus y square plus zx. Similarly we subtract dy minus dz in numerator, and denominator we subtract y square minus zx and z square minus xy. Similarly we find dz minus dx. When we simplify all the terms, the common term x plus y plus z are cancelled, and we have dx minus dy upon x minus y, dy minus dz upon y minus z dz minus dx upon z minus x. So now we see here we can easily integrate these terms. When we take first two terms, we have the integration log x minus y equal to log y minus z plus some log c1. By applying the property of log, we get x minus y upon y minus z equal to c1. Similarly, we solve another two terms and we get y minus z upon z minus x equal to c2, and write the solution as function of u comma v equal to 0. So this is the Lagrange's method when the variable can be separated easily. If it is not possible to separate the variable, then we have to follow the another method, and the another method is method of Lagrange's multiplier. In this method, we just write auxiliary equation as usual, dx upon p equal to dy upon q equal to dz upon r. In this method, we choose Lmn as Lagrange's multiplier, where Lm and r constant or maybe function of x, y and z. We choose Lm in such a way that when we multiply L to first term dx upon p in numerator and denominator, and the second term dy upon q to m, and the third term dz upon r is multiplied to n, and we add a numerator as ldx plus mdy plus ndz and denominator as lp plus mq plus nr, and lp plus mq plus nr is equal to 0. So we choose the multiplier Lmn in such a way that the denominator lp plus mq plus nr becomes 0. So here we have four equations in auxiliary equation. Four terms in auxiliary equation such as dx upon p, dy upon q, dz upon r, and L dx plus m dy plus n dz upon 0. So when we solve last two terms, that dz upon r, L dx plus m dy plus n dz upon 0, we get L dx plus m dy plus n dz equal to 0, and when we integrate this term we get u equal to c1, and we choose another multiplier as L1 m1 n1 in such a way that L1p plus m1q plus n1r is equal to 0, and we get another solution as v equal to c2, and the combined solution is given as fu comma v equal to 0. Let's see the example. X z square minus y square del z upon del x plus y x square minus z square del z upon del y equal to z y square minus x square. It is again in the form of p plus q equal to r. We write the auxiliary equation, but we see these terms are not easily separable. We cannot easily solve any two terms. So we choose the multiplier as xyz randomly and just multiply the first term x. First term by x, we have x dx upon x square z square minus y square. Similarly, the next term is multiplied by y and becomes y dy upon y square x square minus z square, and the last term by z, and we have z dz upon z square y square minus x square. We adding numerator and denominator terms, we get x dx plus y dy plus z dz upon 0, and on simplifying we get x square plus y square plus z square equal to c1. So this is first multiplier, and We again choose another multiplier to get another solution. Let the another multipliers are 1 upon x, 1 upon y, 1 upon z. We just multiply the term, first term by 1 upon x, second term by 1 upon y, third term by 1 upon z, and adding the numerator term and denominator term, we get dx upon x, dy upon y, dz upon z upon 0. So when we integrate this term, we get log x plus log y plus log z equal to log c2, and applying the property of log, we have x, y, z equal to c2, and at last we write the solution x, y, z is equals to function of x square plus y square plus z square. So today we have learned Lagrange's multiplier method. That's all.